Hey, all right. Our last topic for this week is A5, getting up there now. This is an HL topic, and it's called neuropharmacology, right? So this is where things get, I think, pretty interesting. We've got pharmacology. Obviously, we're talking about manufacturing drugs, medicines, things like that. And so, I'm just gonna dive right in. This is a lot in one slide. Don't freak out. Don't freak out. But we've been talking a lot about neurons. We're talking a lot about synapses, and there's this obviously this connecting point right here where one uh, nerve connects with another. We call that a synapse, and recall that the axon ends with the axon terminals, and those various terminals can then synapse a few times. But one thing that I did not go into before, it's too much too soon kind of thing, is that your postsynaptic cell, the cell that's like being stimulated, is actually going to synapse with a lot of other cells, right? And so if this cell is synapsing with, three or four or five or six different neurons, they're all going to have their own type of stimuli. And so basically, we think of these neurons as releasing one of two types of neurotransmitters, right? You can either have what's called an excitatory neurotransmitter, which will excite the next cell, and so that will cause depolarization, which is our action potential. Yeah. Or on the other hand, you could have inhibitory neurotransmitters released by an inhibitory, neuron, which would then cause hyperpolarization. And if you forgot what that is, on the action potential, the hyperpolarization is when we go up for depolarization, down for repolarization, and then we're down below resting potential. That's when the nerve is hyperpolarized. So if you have a hyperpolarized nerve cell, it cannot fire, cannot send communication. Yeah. So inhibitory neurotransmitters will basically shut down your neuron. Okay, so this matters. We have to start here because when we talk about pharmacology, when we talk about the drugs that affect your chemistry of your brain, it all has to do with what kinds of neurotransmitters are either blocked or released in greater quantities. So basically, what happens is this postsynaptic cell, as we've talked about before, it's got to reach a threshold potential. So what happens is because this nerve is synapsing with multiple neurons, some of them may be excitatory neurons, bringing you closer to a threshold, and some may be inhibitory neurons, bringing you back down. And so, what we have to do is consider all of the stimuli, adding them together to see if that gets you enough to hit that threshold. And the name for this concept is what we call summation. Summation, right? You're summing them all up, you're adding them all together. So, if you take the summation of all of, oh, so by the way, let's say of all of the stimuli, the excitatory stimuli, the inhibitory stimuli, you add it all together, is that going to be enough to hit the threshold? And if you hit the threshold, right here, hit the threshold, then you'll get an action potential. But if you have some excitation and some inhibition, and it evens out to be here, you're not going to hit the threshold, the nerve might not fire. By the way, I'm at my house, clearly. So there may be some outside noise, some birds, some cars, and just, you know, enjoy the ambiance. So back to this idea of summation. A nerve impulse is only initiated. In other words, the action potential will only occur if the summation of all inhibitory and excitatory neurotransmitters bring that cell up to that threshold, enough to bring those sodium ion channels to their threshold potential, and then we get our action potential. Summation can also refer to a single presynaptic cell releasing neurotransmitters several times. So if that presynaptic cell is just blasting it with more and more and more neurotransmitters, that could give us a few sort of excitatory transmissions like that, right? So no matter what, summation is the idea that the postsynaptic cell is not just getting one stimulus, it's getting multiple, and they have to add up to the threshold. Not so bad. Okay, the next idea is that we have neurotransmitters, and there are all kinds of neurotransmitters from all of your different types of neurons. We've already discussed one type of neurotransmitter, which was acetylcholine, and that one is mostly involved in movement, right? So muscles, and actions, things like that. But there are all kinds of neurotransmitters. And we think of them as belonging to these categories here as being fast acting or slow acting. Um, and the rough idea is that a slow acting neurotransmitter is going to take longer to have an effect, but those effects could also be longer lasting. So you're not going to get a rapid response, but the response that you do get may last for a longer period of time. And so, if you want to basically increase memory formation, things that you want to have a long lasting effect, you're usually talking about neurotransmitters that are slow acting, that will have sort of a lasting effect involved in memory, things like that, neuroplasticity, learning. Talking about slow acting neurotransmission. Faster acting neurotransmission, these are things where you want to have a quick message that we don't need to linger, we just need to get it done, right? So if we're talking about simple coordination of movements, we're talking fast acting neurotransmission then. Okay. Next concept. So what we're focusing on today really is how drugs can influence neurotransmission, right? And so anesthesia is one such example. Anesthesia basically is when you're going to have a drug administered which blocks down sensation. The idea is that you don't feel something so that during an operation you're not traumatized by all of the pain. And there's two versions. We have your local anesthesia and your general anesthesia. And if these words are old to you because you're interested in medicine, cool, enjoy. But if this is new, it's not hard. So local anesthesia is going to cause loss of sensation in just a small area, right? So you're gonna maybe you'll get some local anesthesia for dental work. They just inject you with something in your cheek or your gums, and then that local anesthesia will numb just that area, but it's not going to knock you out. You won't be sleeping. You'll just be numb in that area. General anesthesia sedates the entire body. This is the kind of stuff that puts you to sleep. You may lose consciousness, or you may go into what's sort of like a twilight state where you're maybe awake but not fully aware. And no matter what, both types of anesthesia are going to work by interfering with neural transmission, right? So those neurotransmitters are perhaps going to be blocked in some way. And so then what happens is your sensory perception. So you may be injured, yeah, right? So like the doctor slicing through you, that ought to hurt, and it physiologically has the same change, but your brain cannot interpret that pain messaging. And so the transmission from the sensory part of your body and the peripheral nervous system does not make it to your central nervous system to interpret that as pain anymore. Something is blocked in those synaptic pathways with the neurotransmitters. So let's take a closer look at how that synaptic transmission can be blocked. Okay, here's one example. And this is actually a more natural example. So not necessarily a drug, but more to do with how your body can experience a sense of euphoria and have sort of a natural pain numbing, right? And they're called endorphins. So perhaps you've heard of endorphins before. If you're into exercise, you go for long runs. If you're happy, certain activities can bring on an endorphin rush. And what these endorphins do is they're going to block the normal transmissions that are involved in pain reception. So normally a signal is going to be sent from one nerve to another. There'll be a synapse from one nerve to another, and this synapse will use a neurotransmitter that's involved in pain reception. So this is a sort of a chain reaction of neurons and the pain response, right? So what you need to do is if you want to stop feeling that pain, you need to block that transmission. And endorphins are naturally occurring chemicals in the body that shut that down. And so there are special little receptors on this presynaptic cell, and those little receptors are called opiate receptors. And you've heard of opiates before, right? And so these opiate receptors will bind to the endorphins that your body is making. And then that will basically shut down the release of transmitters. There's no communication with the postsynaptic cell, and that message of pain never gets from your finger up to your brain. Hope that makes sense. If you need to, take a second and pause me and just kind of review all the stuff we have on this slide. So you can probably see where this is going. So imagine if you had a chemical, a synthetic chemical, or some maybe from a plant, that mimics these endorphins, right? So all that you have to do is get a chemical that behaves very much like these endorphins, can bind to those opiate receptors, and then you will also have the same feeling where you will no longer feel the pain. And so pain medications like opiates are designed to mimic the endorphins, bind to these receptors, block the transmission of the bad feelings, only allowing the good feelings to come over your body, and then you get the sense of euphoria and happiness, and there's a quote high attached to that, along with the lack of pain that's normally being transmitted by these neurons. Okay, and this brings us to the last and perhaps the big point of this section, which is drugs, psychoactive drugs, including caffeine, right? So psychoactive drugs could be harmless like caffeine, or they could be, the hard stuff, and we'll talk about both. Let me get my face out of the way. Ooh. Okay, so psychoactive drugs, they're just medications, drugs, that either increase or decrease postsynaptic transmission. So again, that's the transmission from the beginning of the presynaptic cell to the postsynaptic cell. And they do that basically by mucking up the behavior of your neurotransmitters. So if your neurotransmitter cannot talk to the postsynaptic cell will not talk to your brain. So that will affect your brain chemistry and the way that you behave. And we have two types. Sometimes people call these uppers or downers. And so basically the idea is that you can have an excitatory psychoactive drug or an inhibitory psychoactive drug. And these, if they're excitatory, they're going to increase transmission. So you'll have more going on, right? If you're having an inhibitory drug, they're going to decrease transmission. So that would cause hyperpolarization, and that will shut down types of activity. So think of somebody with THC. This is the stuff that's found in marijuana. THC, right? You're shutting down, you can kind of guess, you're shutting down some of their neurotransmission, right? You've got alcohol, same idea. Valium is a sedative. On the other side, some popular excitatory psychoactive drugs include caffeine, cocaine, nicotine, and amphetamines. So for your exams, you need to be able to name one such psychoactive drug and identify whether it causes an excitatory or inhibitory response. And this is a very safe list that you could use. So pick one, commit it to memory from each category. Name one excitatory and one inhibitory psychoactive drug, and know that it is inhibitory because it decreases neurotransmission, or is excitatory because it increases neurotransmission. And then IB would like you to know one specific named example of a psychoactive drug. So these are like choose your favorite on this slide. Moving forward, we're going to talk about this one particular psychoactive drug called MDMA. Perhaps you've heard of MDMA. This is the active ingredient that you find in ecstasy, sometimes called Molly. And sorry, I guess I need a more appropriate slide if you can see what I'm talking about. But anyway, if you take a street version of this drug, which you really shouldn't do because street drugs are not safe because you don't really know what's in them. But if people take what's called ecstasy, basically you have this stuff, the MDMA, laced with other drugs, amphetamines, speed, things like that. And so first I'm going to talk about what MDMA is, how it works, and then we'll go back to this idea of the street variety, which is the stuff that gets you into trouble or in the hospital. So MDMA is a psychoactive drug. And I think this might be a GIF. Let me pop this open and see if it works. Sometimes it works. No, not going to work for me. Okay, go back down. MDMA, it's a drug, and it increases the activity of a neurotransmitter called serotonin, and another neurotransmitter called dopamine, and another one called norepinephrine. And so what these neurotransmitters do is they basically give you this rush of euphoria, of welcoming, of positive feelings, yeah. And so this sort of there's a twofold thing here. So MDMA has been used for really important research for people who have post-traumatic stress syndrome, PTSD. So there can be some positive applications of this drug. People with PTSD under